Thank you very much. So I am Augustin Parjadis from Polytechnique Montréal, and I'm here to present my work on the dynamic ride-hailing problem, for which we developed reinforcement learning solutions and heuristics. And this work is joined with Quentin Capard and Louis-Martin Rousseau, also from Polytechnique Montréal. So the ride-hailing problem has been well introduced, so I'll be quick on this. But we're dealing with a fleet of vehicles that have to serve randomly arising requests. And so this is a popular problem and ever increasing popularity with the rise of connectivity of drivers and potential clients and successful apps that connect them. And on a more mathematical point of view, the challenge is twofold. So the assignment of arising requests of drivers to assigning arising requests, and the repositioning of vehicles to idle to lots. So I'll start by presenting some heuristic that we use as baselines and how we can use reinforcement learning for fleet management for those two challenges. Then a quick look at the results. For baselines, I'll start with the assignment problem. So like in the previous presentation, we just used a very natural solution of choosing the closest vehicle to the arising request. This is a greedy heuristic that we are going to try to beat with learning, but it is pretty performant because quite natural. And so this is the first baseline we have. The most interesting part of the problem, I think, is in the repositioning problem, because there's a lot of possibilities and we're dealing with the uncertainty with the demand. So when a vehicle has finished with his job, it has to be repositioned to a lot in the city. Multiple things has to be considered. We want to ensure wide coverage of the city because requests can arrive from anywhere. But we also want to focus on zones that are quite active because the demand might be concentrated and is concentrated in some spots, as we saw before. And so these are two considerations to balance. And we might also want to avoid unnecessary long travels for the vehicles. So our heuristic wants to first predict the future demand and then ensure coverage for this prediction. Here on this small diagram, the diamonds represent potential lots for relocation and the squares, the prior demand. Because this is my first step, we start by sampling prior demands with bias towards recent demands that will represent more accurately what will happen at the time of consideration. And then we'll try to find the lots that will minimize the distance of the pairing of prior demands to the closest vehicle idling. I'll give a little more detail about that, but this is what we are trying to do. And then we'll also check for vehicles that have been idling for a long time to relocate them to more busy areas. Might have been a relocation error. So in our case, we might want to choose the diamond I highlighted here, pointed by the arrow, because even though it is not a lot surrounded by the most prior demands, a vehicle is already present to the busiest lots. And so we might want to choose the second busiest or unattended lot with a lot of prior demands next to it. We translate this by this problem. This is basically a small minimization problem over the lots. And we're trying to minimize the distance of sampled prior demands to the next closest vehicle. So here, those are the pairings on the diagram. And so the lots highlighted for relocation was correct here because it's minimized the pairing. So this is what we used as a heuristic for the repositioning problem, and it worked pretty well, but how can we try and beat this with reinforcement learning? So we also had a small introduction on reinforcement learning. Basically, we're having an agent interacting with an environment to try and maximize expected sum of future rewards. And so the agents observe the state of the problem, take an action after that observation, and gets a reward as a result that would quantify the quality of its behavior. Then the state will be modified by the action, and the agent will have chosen a new action, etc., etc. In our case, the state of the problem was defined by lots of data that we put in a big vector. We were interested for first the assignment problem in the time of the day and the day of the week, information about the 10 closest vehicles to the rising demand, and information about the demand. So there are many ways we can define the state of the problem, but we want to give probably as much information as possible for the reinforcement learning agents to learn well and to do informed decisions. The action it will take will be choosing simply a vehicle among the 10 closest we gave information about, or to reject the demand. And the reward will be the earnings from the whole fleet during n step with n fixed. We do not use the earnings just one step forward because the delayed gains have to be taken into account, and it's easier to learn this way. We chose for our agents a deep neural network structure with a self-attention layer to kind of process the data. The diagram here is just a small representation of the network. And then we trained it with the n-step double Q learning. The self-attention layer is used to be able to extract more information from the state we give an entry to the agents. Here are the training curves. So we are seeing in red the random. So our agents started with a random performance because they didn't learn anything yet. And we're trying to beat the green line, the greedy algorithm for assignment we saw at the beginning. And we see that with the blue line achieved that. So this is the agent with the self-attention layer in the structure that helps in the expressivity of the model. And you can see that we can beat the greedy algorithm not by much, but there's not a lot of room for improvement on that simple assignment problem. But this was a successful attempt at learning to assign, and this is what we use for our submission. Now for the harder repositioning problem, the state. So we designed another learning algorithm and a different agent, specifically for this time the repositioning problem. And so it will be the environment will be defined a little differently. Here we gave information about the lots and not the vehicle. And so we gave information about the number of vehicles already idling at a given lot, information about prior demand, and information about the vehicle to relocate. And this time the action will be to choose a lot or a zone, depending on how we define the environment, to relocate the vehicle. And again, the earnings for the reward. The agent structure was pretty much the same. Instead, we tried also more advanced deep learning structures with the graph neural network or set transformer, but that wasn't really successful. So this is what the training looked like. This time the random baseline is in orange. We're trying to beat the heuristic I presented in green. And as we can see, the agent in blue tried to learn something, but it didn't work. We have the exploration for this problem. So the agent has to explore the possibilities it has to then maximize and exploit the best solutions. But the exploration phase seems to be difficult. We noted that the agent was successful in identifying the active lots to relocate to, but then focused on always relocating vehicles there, which is not a great solution because even though it ensures coverage of a hot zone, it's just the whole city is then left out and a lot of requests are missed. several things have been tried to try and correct that training. We have tried to simplify the environment by having less zones or lots to relocate to for easier training, trying to simplify or enrich the state representation, trying different kind of exploration or group research, etc. But during the time we had to try and learn for repositioning, we didn't succeed in learning much better than just a random strategy for repositioning. It has been noted that a random strategy is better than just focusing on one lot because it will at least ensure coverage of the city, which was better performance-wise. So for the results, our name is CorailRPC, and we use the deep reinforcement learning agent for assignments because training was successful. We kept the heuristic I presented first for group positioning. And so we arrived on the second place on small and medium instances. Congrats to the first team for their performance. So this was, we're still happy with that success, even though repositioning was hard to apply reinforcement learning to. And sadly, some inefficiencies in the code made us not able to compute all of the large instances. You can still see here that we submitted results for 2 instances and that our results held if you're able to compute them, which we're now able to do since the code has been corrected. In conclusion, we presented a solution of a learning solution for the assignment problem and a repositioning heuristic that tries to forecast the future demand using prior demand. That was quite successful, but a lot of improvements could be made to, so of course the learning parts that I'll keep trying to improve, but also the heuristic that was just developed as a baseline. And for example, the traveling distance of the vehicle to its relocation lot wasn't taken into account. And because it has an impact on the earnings, it should be considered, as we saw in the previous presentation. I'm at the moment working with an industrial partner for application in emergency services, so for ambulances. This is pretty interesting because we have the same kind of problem, but the incentives are pretty different. We're not trying to maximize a profit here, but more trying to maximize the the successful fulfilling ratio, because we cannot leave emergency out because they're not profitable. This is not the same kind of problem. So thank you very much for your attention, and I'll be here if you have any questions about our solutions. Thanks.